hear me? You tell you if it's not. Is it turned on?
Should be on. Okay, good morning. Welcome to the second brief lecture. So I will talk about what I call gradient dynamics formulations of film equations. And so what I will do in the 3 times 45 minutes, 1 time today and 2 on Friday, is talk about let's say starting with a simple system like a thin film or droplet on a solid substrate, and the film consists of a simple liquid. So this will directly connect with what Len did, let's say, using density function theory and at the end giving an outlook towards the thin film model. So I will rephrase this slightly differently and discuss a little bit the example of dewetting of a thin liquid film, so when it goes to dewet the substrate. So if you read the abstract, I sort of separated model formulations from examples. I now in the actual lecture I actually mix this to make it more interesting and not, let's say, lose you while developing the models. And then in the second lecture I will then start to discuss mixtures. How do we formulate these systems for mixtures, and give some examples for deposition patterns where one uses such models to describe those. And in the final lecture I will focus on an effect rather than model types. I will talk about depinning transitions, for instance, when a droplet gets stuck at a hydrophobic patch, how it behaves when you force it over this patch by critical force, right? Force out so, that's what is the plan. So what is a good starting point to explain what one wants to describe are these experiments by Günther Reiter, published in the early 90s, where you have a thin polymeric film. So this is a top view already right into the experiment. So you have a film that is, this one is 40 nanometer thick of polystyrene. It is spin coated in solution on a substrate, then the solvent evaporates. It's still, let's say, at room temperature. Then you have a ultra thin flat film and you bring it into an oven. Above the glass transition temperature it becomes liquid, and then it suddenly realizes it doesn't want to be on this substrate because it's energetically more favorable to collect in a big droplet. However, as this is a very thin film, the hydrodynamic process of receding the entire film in a single droplet would take probably centuries. So what it does, it forms these holes in the film. These holes grow in time, then form this polygonal network of liquid rims, and this then can decay into this rows of droplets in a plateau radial instability. So, and there's a lot of work done in the 90s and later on about the rupture of the films, the growth of the holes. Can these moving fronts of this that have to move outwards, can they become unstable? What are the conditions for that? And then there are geometric analysis of this type of random networks, and then people study also the decay of liquid ridges on homogeneous or heterogeneous substrates. And to do all this, you need dynamical theory, right? So you need a dynamical theory that takes into account the wettability of the substrate and the capillarity, because these are the main driving forces, right? This is ultra thin, so no inertia at all. It's all overdamped in a Stokes flow. Now, a more recent experiment is here of the group of Karl Jacobs in Saarbrücken, where they look at, again, ultra thin films. So these are really thin. These are below 10 nanometer thickness, and actually the difference between the two is, I think, 1 or 2 nanometers only. Again, polystyrene, it's like the guinea pig of this type of experiments. And what you see here, if you have the thinner film, you find this sort of more or less homogeneous array of little holes developing, and it's called the spinodal process, in equivalent to spinodal decomposition in if you have a binary liquid or binary phase that decomposes into 2 components, because it has some similarities. This is called spinodal dewetting. And then this is a nucleation process. So here you have holes that are sought to form at defects. They grow, and here you see this, that outside this moving rim you find something that one could call a secondary nucleation, where you find this ring of secondary and tertiary holes developing here. And there are very nice simulations and studies with this type of equation, for this type of system, with again, these thin film equations are shown. If you want to talk about this particular thing, there is Günter Grün at the back, who was involved in those projects with Karin, and is probably glad to talk about this. Now, this is sort of the simplest model. You just have a film on a substrate, no additional forces included, but there are many varieties of this experiment. So this is one done by the group of Uli Stahler before he moved here to Cambridge, and what you see here are atomic force microscopy images. What is the length scale? I think these are 80 micrometer, these are 80 micrometer. So that on the previous slide, this was also atomic force microscopy, maybe 20 micrometer in the lower row and 5 to 10 in the upper row, where the very first slide was optical imaging. So what is done here, you have again a thin polymer film, but this time it wets the substrate. So you have it liquid, you can actually anneal it. This is important to exclude the question that comes, is there still a pre-stress in this polymeric film? Will this cause the de-wetting and so on? So you can anneal these films, and then you bring them into a strong electrical field. So we talk about capacitors of, I think, 100 or 200 nanometer gap width, and then you can produce extremely strong fields. This destabilizes this dielectric liquid, and you can find this column forming that sort of span, the space between the lower and the upper plate of the capacitor. And this is another example where they find this. And also this type of structures one wants to study this situation. So the systems I showed up to now were on a horizontal substrate, so no additional driving forces laterally to the substrate. However, you can imagine you incline the substrate. Now for this nanometric systems, not much would happen, right? Because the driving force would be very small on this length scale, gravitation, if it's gravitation. But if you have a macroscopic drop, so millimetric drop, like here, this experiment by the Lema, and you put them on an incline, you can see that these droplets at different inclinations, they change their shape from oval to sort of having a cusp at the end, and then this cusp can emit satellite droplets. And if you want to talk about this system, you need to include these driving forces into a thin film equation. I will not talk about this system, but somewhere here should be Jens Egger. He's around. So if you want to talk about this system, Jens would be a good person to talk to. So now, this is assumed to move smoothly down the incline, but you need a very smooth substrate for this to happen. If the substrate is rough, then the droplet might get stuck and pin and so on. And there's an experiment here by Schäfer and Wong from '98, where they study just the rise of a meniscus in a thin capillary, right? So a glass tube. And what they plot here is the height of the meniscus over time. And you would expect, I think it's probably measured the other way around. So this is a capillary rise approaching an equilibrium height here. However, it's not a nice exponential as one would expect from the so-called Washburn law. It looks like an exponential, but with a lot of steps. Right? So what happens here, this contact line gets stuck, like here, it stays horizontal, and then it slips, then it gets stuck again. So it's a stick-slip motion, and people also think this is related to heterogeneity. So we come to this with this liberty. So let me keep that on. I will not talk about it. So now let's go to the simplest system, just thin film on a horizontal substrate. So Len has already talked about statics, so I can say this only very briefly in a slightly different way. So if we have, let's say, such a heap of liquid on the substrate, and we want to know what does it do in equilibrium. Right? So what we would do, we would write down the energies for the liquid solid interface, the liquid the solid gas interface, and the liquid gas interface. So we write down, let's say, this macroscopic energy, where we have we integrate over the length of this droplet, have the solid liquid interfacial energy, and then the liquid gas one, where I put this geometric factor, what is the ratio of the dx along the substrate and the ds along the interface. This is somewhere written here in 1D, is this factor here. And for the part outside, so we assume we have a fixed domain D that can be arbitrarily large, and we can let this go to infinity. but this gives the contribution of the outside interface. And we put a finite amount of liquid on the substrate, so we need Lagrange multiplier lambda that conserves our weight. So if you minimize this energy, you get a bulk term, it's the Euler-Lagrange equation, and this gives you the Laplace pressure, the pressure jump between the liquid and the gas phase, and it just tells you the pressure jump is surface tension times the curvature, as then derived with the density function. However, you get also boundary conditions at these 2 points, and these boundary conditions are the Young-Laplace equation, where you can see this zoom here. It is essentially a force equilibrium if you see the surface tension as a force going away from that contact point. You say this is a force equilibrium where this interface, I call here gamma, the interfacial tension, has to be projected down on the horizontal. This is cosine theta. Yeah, so this is the famous Young-Laplace equation for that. So this is a macroscopic picture. Now, if you make your film very thin, or you want to know what happens really close to the contact line because something is at odds, if you take the macroscopic picture, you can't do dynamics then. So you want to go from, let's say, a stick film where you can well separate the solid liquid and liquid gas interfacial tensions, and then you go to the solid gas where you just have the interfacial tension of this interface. However, if you make this film thinner and thinner, these two interfaces will start to interact at some point, and you need a correction term that sort of extrapolates between this energy and that energy if you want to have a continuous transition. And you can do this by saying, okay, let's go from this sum that describes the energy per area in this situation. Let's go to the same sum, but now let's add some term that depends on the film height. You can call this a wetting energy or net lesion energy, and it will turn out that this is the same film surface substrate interaction energy that Len introduced, and its derivative is a disjoining or diagonal. So now from this macroscopic energy that we had on the previous slide, we would now write down something I could call the mesoscopic free energy. So it has the interfacial tensions of the solid liquid and the liquid gas interface, but then it has now also this wetting energy, and still we need to conserve the mass. So this time I write it in terms of a mean height. So a word about the name here. I had this discussion with Len. So technically, mathematically, it should be called the Lagrangian because if you minimize it, you get the Euler-Lagrange equation. However, as in, let's say, the wetting community often calls it interface Hamiltonian because it derives from the microscopic Hamiltonian. So I will stay neutral and I will just call it from now on free energy, right? Even if it's a interface Hamiltonian. And now what happens for partially wetting liquid, if you put the right wetting energy in here corresponding to the discharging pressure that Len had on one of his last slides, you would go for partially wetting liquid, that means one with a finite contact angle. You would go from this sharp point here where the three faces meet, you would go to such a picture where you have an ultra-thin precursor film of, let's say, a nanometer that can coexist with a macroscopic wedge of this macroscope. Now this is static. What we want to do is dynamics. But before we do that, I also show you the discharging pressure that Len had, and you see already, if you remember that graph of Len, it was flipped around, right? And this points to one problem in the literature. There are several different sign conventions around what you, so whether you write the discharging pressure as a negative of the derivative of this wetting energy or with the plus sign. And so there are several places where you can define your sign in different ways. So be careful and never mix things from different papers, even if they are from the same author, because they might switch sign. For instance, Deschênes switched sign in between papers, what confused me highly. And I think Len and I, we use different signs, but we have a common paper, and I don't know which sign we actually use there. So I would need to check. But the physics is the same. So you have the pressure over the film height. In a wetting situation, it's this black line. So there's no minimum at low film height. So there's no tendency that the film wants to get thin, and then it has, because of mass conservation, to coexist with the macroscopic properties. This would just thicken. Right? So and then the red curve is this partial wetting case, where this point here gives you the thickness of this precursor film that coexists with the macroscopic. So typical choices that you can find is long-range van der Waals interaction. So this would give you the pressure 1 over h to the power 3. Then the one that Len introduced is some constant over e to the power h to the power 6 for as a short-range part of the. So this gives you this upwards tendency here. And there are other short-range terms that are discussed in the literature, for instance, for this exponential, often used by Sharma, for instance. So that's the one. I think most figures I have are done with this triangle pressure into this block. But it does not matter too much. There are some subtle differences with choosing this one and this one in this region. And this has to do with the order of the vacuum transition as we want to do. So now if you want to do dynamics in those systems in general, so what would you do? What could you do? I mean, you could say, okay, I know all the statics, I have all the energies for arbitrary contact angles, and then I can look at the second variation of these energies, and this tells me whether they are stable or not. But it does not tell you what are the dynamical modes that, let's say, you know it's unstable, but you don't know what it will do. So an example is if you have an infinite ridge like that lying on a substrate, if you look at the energetically most dangerous mode, it's the one of infinite wavelengths, dragging all the liquid to a single drop. But if you do the dynamic calculation, what you find the dynamically most unstable mode is the one where the wavelength is of the order of the magnitude of the diameter of the. So this gives you, this tells you, this approach would give you the stability, but not tell you what the system does. Now you could say, okay, let's take Navier-Stokes or Stokes equation with a free surface, and I think Andrew Hazel who's sitting there, has a very nice code to do this, but and he might protest. But I mean, I would say it's a high computation effort, and there are nearly no semi-analytical results, and one has to do some ad hoc stuff at the contact line that one needs to discuss. And the list of names is about 10 years old, so some names should be added. So then there are also, I think that's probably solved nowadays. I mean, there were a lot of tracking issues for the free surface. I mean, really to track what the free surface does was, I think, very difficult 10, 15 years ago. So you would then maybe opt for Navier-Stokes plus a phase field for the transition liquid gas. But this makes it even more tricky numerically, and you have them to do a lot of fun. What I will vote for is the so-called long wafer replication approximation. So you pay a price. The price is that you can only look at small slope interfaces. Right? So you can look at shallow droplets or at films that develop a long wave instability. That's the price you pay, but then you can include nearly everything you want. You can include wetting properties, the contact line motion. You can include additional temperature gradients, electrical fields. So it's all sort of possible, and you can also use then a lot of tools from dynamical systems theory to actually analyze what happens. So I will not show you the derivation of the equation. Actually, Michael sketched it yesterday. I just tell you what the steps are. So you take the full equations plus boundary conditions and continuity equation. Then let's say you scale to obtain dimensionless quantities, and then comes the important step. You need to introduce this long wave scale. Right? So you say, I have a typical length scale in vertical direction, let's say h. And I have a typical length scale in lateral direction along the substrate, let's call it capital L. And these two should form a small ratio epsilon. That actually for droplets is of the order of the contact angle, right? So this also should be small. And then you can do a series expansion in all the fields, for all the fields, and solve this system order by order for the velocity and pressure profile. And if you rescale your dimensionless numbers in a clever way that keeps the terms that you want to keep, and that's actually would be a lecture by itself to discuss that. you get a nice film thickness equation already to highest order in the. And what does it look like? It looks like this. I think Len had it already on the slide, but let's go through it. So we have the time change of a film thickness profile H is equal to the gradient of a flux. So this is just continuity, mass conservation. Then we have this flux is a mobility that I call Q of H times the gradient of a pressure plus some driving term. So this mu tilde is some lateral driving. That could be being on the incline, could be a lateral temperature gradient or versatility gradient on the substrate and so on. And now this is the gradient of a pressure, and the pressure has two parts here. It has gamma Laplace H, what is Laplace pressure? This is curvature pressure. And it has an energy scale kappa here times the discharge of the radiating pressure, and I already indicated we can make this also x-dependent to get a wettability pattern on the substrate. Now if you assume no slip boundary conditions at the substrate, what you end up in this long wave derivation, you get for this mobility in h to the power 3 over 3 times the viscosity. Now what is this capital pi? So I just put some examples. If I just hold this an additional pressure, then I could pick the term I had on the 2 slides before. And this would be the radiant pressure for wettability. If I put this one in, that's the one that Len had rescaled. However, curiously, if I just put this polynomial in, and I set Q to be a constant in what we have there as the Cantor equation for decomposition. So this indicates already that there are deep relations between the two. And curiously, if you look at the heated thin films, and you look at the long wave instability of you get actually the correct equation if you plug this term in, but it's sort of an accident, I think, because this is really feeding energy into the system, and you would, let's say generically, you could think, why are there no oscillations going on? This is just sort of happening just in this particular way. If you plug this one in, you have the film is electrostatic field. There are many of these different terms. Now let's take a different view on this equation. If we just said, okay, we don't know anything about hydrodynamics. We just know this is a film thickness field, and I want to describe its dynamics, and I only know there is some wetting energy, there is some surface energy, and the film height is the mass is conserved, so it's not volatile, right? What do I do? So then I look, what are the most simple equations to describe the evolution of some order parameter field? So if we take a single conserved order parameter field, that would be a Cantor type dynamics, and you would write such an equation. You would say, okay, it's conserved, so there must be continuity, a mass conservation, so it's a transport law for this conserved quantity phi, time change of phi is equal to the gradient of the flux, right? That's our conservation law. And then the flux should be some mobility times the gradient of some thermodynamic driving force. So that this gradient is this thermodynamic driving force, and this driving force should be the variation of the underlying energy, right? So the only thing that we need from equilibrium, we need some F. And then where all the dynamics is hidden is here the Q. Now the equivalent equation for the non-conserved case is written down here, so this would be an Kahn type equation. So now our phi is not conserved. And then you would say, okay, that's a steepest, let's say a steepest descent dynamics. So you have the energy functional, you take the variation, that would be like the steepest descent in this infinite dimensional function space. And there's some mobility in front, could be constant. I call it here Q non-conserved. And note the sign difference, and ask me in the break if you want to know why there has different sign. Essentially, this if you want to prove that F decreases in time, you need to put here positive sign and the negative sign. Right? Then you actually know your dynamics goes to the minimum of the. So now I motivated this equation. So if we write it down for our film height, now I copied just the equation over from the previous slide. I just replace phi by h, what is our film height. So that should be the general form of the equation. So what is our energy? So I had introduced this interface Hamiltonian of the energy as a mesoscopic energy. So let's try out what happens. So if we put, now I'm cheating, I replace this factor psi. That was 1 plus pxh square root. I replace this by 1 plus 1/2 px. Where so I take already a small slope approximation somehow. And then I drop the 1 because the 1 will not contribute to the variation anyway. Right? So I replace this factor psi by the square of the table. And then I have the wetting energy. So if you take the variation of this, from this term you get a minus Laplace squared. So you have a Laplace h, the minus is out here. And from this term you get the negative of the discharging pressure. dF by dH is the discharging pressure, so minus sign out here, so here's the discharging pressure. If you compare this equation with the one I had 2 slides before, that you get in, let's say, 2 pages. I think if you did it once before, then just do 2 pages to get it. I mean, this looks much easier. So where's the catch? The catch is the Q. You can't really postulate what the Q is. So you need to do all the asymptotics to get the equation and to get the Q. But I mean, this now allows to say, okay, if I change something in my energy function, and I assume all this dynamical part remains the same, I can easily expand this equation to other cases. So now we have the equation. So I want to, in the final minutes, I want to just sketch what are now things I can do with such an equation. And I use this case of a film on a solid substrate because it's probably one of the simplest cases to look at. So what would you do? I mean, you have this nice PDE. You can study full dynamics in time, so you could start with any initial condition you want and then just see what happens. But I mean, the better way is to analyze it step by step. So the first step would be take a flat film and look how it behaves under perturbation. Right? So you want to do a linear stability analysis. You would write down an ansatz for your film height h. Let's assume your base state is h0 is a constant film height, and then you add a small amplitude perturbation, and I write here harmonic perturbation as an exponential with a small epsilon in front. That's not the epsilon of the long range approximation with epsilon. This beta is the growth rate in time of our mode, so if this is positive, we are unstable. If it's negative, the situation is stable, and this k would be the wave number of the situation. Now, if you put this into your thin film equation and you expand in epsilon, you get to linear order, you get the equation that relates beta and k, and that's called the dispersion relation. And I should have a plot underneath. So you see, it's a quartic expression. It has a k to the power 4 term and it has a k squared term, and it has a critical wave number that you can write as the negative of the second derivative of this wetting energy. So you know if this function f has an inflection point, then stability changes, and if it is stable, you have the blue curve, so it goes down, beta is always negative, and if it's unstable, you have a k squared going up here and the k to the power 4 going down here, and you have the critical wave number there. Now, what I will need on the next slide is the knowledge that whenever I have a critical wave number in such a dispersion relation, I know on general grounds that there is a non-trivial branch of solutions, of steady-state solutions, branching off the trivial branch of flat films. Right? So assume I take the domain size as a control parameter. I have, for any domain size, I have a flat film as a solution. But then I know here I have a critical wave number, so at the critical domain size of 2 pi over k, there must be a new branch appear. Right. Now, before I do that, I show you the stability diagram for the discharging pressure I introduced before. So this was the combination of the exponential and the power law. So there was this little parameter b, and I think it was on top of the 1 over h cubed. And so that would be a parameter where you can switch that discharging pressure between wetting and non-wetting, or partially wetting. And if you go to small values of b, you find there is an intermediate film height range where it's linearly unstable, and then there's a region that you can't see in the linear stability analysis where it's metastable. There you need a finite size perturbation to actually make it rupture. And then there's a region outside here where it's absolutely stable, so you can do whatever you want to the film if you go back to the flat. So now let's look at a typical bifurcation diagram for this situation. So I use the domain size that I called here period, because it's also the distance between droplets if I put several of them on a larger domain. As a control parameter, you could also fix this to a large size and use the little b as a control parameter. So that's a choice that might not be the best one. Anyway. So what you can find in this linear unstable region of this phase diagram on the previous slide, you would see there is a bifurcation and there's a branch coming out there. And there are two different situations that you can find. You can find that this branch goes to larger periods. So this would be called supercritical bifurcation, or you can find it goes backwards towards smaller periods. So this would be called the subcritical bifurcation. And then it folds back here in a satellite bifurcation. And if you look at the stabilities of these solutions and you look at a single period, then you would see these are all stable if you look exactly at the same period of the system. This part here would be unstable and this would be stable. And then if you look at energies down here, you see that this little unstable part here has actually a higher energy than the flat film, right? And so what turns out what these are nucleation solutions. So these are critical solutions you have to overcome to get, let's say, a film that is still linearly stable here, right? If you want to get it to rupture, you need to bring it over this solution and then it will fall down to this. And you see the blue curve. The blue curve has no connection to the trivial solution. So this has stable droplets up here and critical solutions down here. And these are the branches that you find in the metastable region. And we get all this by continuation. And what else should I say here? I was very careful to say these are stable when you fix the system size to this period. However, if you take twice the period, so you have, let's say, or you take this solution, either the red one with these two droplets or these four green ones, and you do a linear stability of those, they are always unstable. Because the energetic minimum for this system that has just this length would be the big blue. Right? They won't, actually I'm not sure they are for different volumes. So do not take it literally. I mean, but these four green ones would like to join in a single one because that's the energy. However, you can change this if you make the substrate heterogeneous, then you can actually play around and stabilize it. But that would be a typical way how you could analyze this. And then you can, I mean, with this in mind, you can go and do time simulations to see whether really things happen that you would expect. If you get nucleation where you expect nucleation and so on. And the curious thing, what happens in, let's say, an experiment, there was a discussion whether if you saw these random holes in the experiment, people would say, okay, this must be metastable. If they saw this binodal pattern, they would say, this must be linearly unstable. However, what we found is if you actually have finite size perturbation, it doesn't really matter whether your thin film is linear, stable, or unstable. You can get a random pattern of holes, or you can get a spinodal pattern if it's if you are, let's say, deep enough in the spinodal region. So let's go back to this plot. We found that it differs whether you're very much inside here, deep inside, or whether you're already somewhere here, because in this region it totally depends on your initial conditions, what you see. But inside here it doesn't really matter. We always see the spinoidal pattern. So how can one understand it? So we have studied for the flat film the linear stability. This gives us a close rate. However, now we have this solution. These are unstable solutions. However, they're actually important because if you have a lot of, you poke little holes, what the system will do, it will try to first get to these solutions because they attract evolutions, because they have only one unstable direction in this infinitely dimensional function space. So they attract infinite minus one dimension, and then they expel the evolution in this one dimension, in this one direction. So if you look at the growth rate of this solution, and you do this by now doing a linearization around the steady states that depend on x. So it's a bit more messy than the thin film for the flat film, right? So you get, however, you can again get this growth rate beta. So if you do this, and you compare the growth rate here plotted over the period now, the growth rate for the flat film, and you compare this to the growth rate that you have in this small region of length. You have a growth rate of these nucleation solutions, and you see, depending where you are, what is your mean height. And these are all, you see, because we have the dashed lines, they are all in the linearly unstable regime. Depending on this ratio of the heights, either this one would dominate or this one would dominate. Right? So if you have, so one could translate it in the following way: if you have a dirty system, if you go deep enough into the, this one, into the spinoidal regime, it doesn't matter. You get the spinoidal pattern. Right? But if you're further outside, if you're somewhere here, then you do not see a spinoidal pattern, even if you're inside the spinoidal regime. You see then a nucleation pattern. And we, let's say, artificially taking the same, when the height is identical, taking this as a border, but it's not, I mean, it's not an exact border. If you plot this into the diagram, you see this gives you this new dotted line in this diagram. And then we distinguished here nucleation dominated and distribution dominated. I mean, I think it has helped to analyze some of the experiments, but it's probably still quite under discussion because it totally depends how you start the system. And I mean, I have it in 1D. A typical simulation would be the following. So I'm in the linearly unstable regime. Film heights are not written down. I guess it's the two. It's this one and that one. And you see, I start with a little dent in both cases. Right? So I do not put. I have, I think, a very tiny noise everywhere in the initial condition, and I have a little dent here in the center. And if it's instability dominated, I mean, it starts. It looks like a wave packet that expands, right? So it starts at that point, but what comes out, you see, this is in units of the fastest growing wavelength. So it really nicely fills it with 16 of them, right? So it exactly gives you the linearly expected results. However, if you a bit closer to this border, then something else happens. You get actually something like a holded form that expands. Then you get this undershooting here, and then this acts like a secondary nucleation solution here. And then you get a secondary hole. And then so it's more like a process of hole formation, a bit expanding, hole formation, and so on. So much like the difference in that I showed in the. So this is rather old results. Also, this is all about 10 years old. And I wanted to use this to accustom you to the way of thinking in how you derive a thin film equation in this case, and how you would analyze it. Right? So I mean, I'm not really a friend of only doing simulations. So if you can do some more analysis, then you can understand this. So we looked at experiments in general with interface-dominated film drop dynamics, and then we looked at the modeling. Long wave expansion is very important. So whenever you see a steep droplet, I should mention that. So that's because that's a common mistake, I must say, of referees, but also even of authors. Actually, if you see that, then normally the protest is, but this is 45-degree contact angle. So this cannot be described by long wave approximation. However, this is in long wave scaling, right? So you have to multiply this by the vertical dimension. You have to multiply by a small parameter epsilon to get a real scale picture. So in extremum, this could be nearly infinite slope, and it would still be long wave. People might dispute it, but and I discussed a little bit the analysis tools. And so on Friday we will start to look at mixtures, and then on what to say? I mean, the issue is that the PDFs and the videos are available only after the talks, and I think maybe even only after the school. So I put the slides on the web page, and I just amended the publication page. So I put it as the first line on the publication page as PDF file. So this would be publication. That's slides on a nice 3x3 format on the A4. You can print it without printing 80 pages.
Okay, questions?
A question. If you go back to your growth rate or dispersion relation as a function of wave number, there, seems that the low k, right, are a group of unstable modes in periodic boundary and periodic domain, and then higher than a certain level of wave number, they're all stable. So do you suppose that if you kept the unstable modes and a few of the stable modes, you could get the same bifurcation picture? So the question is this system essentially low-dimensional? It's in this long wavelength regime of the derivation, right?
I mean, you could try to approximate with some modes, but the problem is you could capture you could do something like an amplitude equation also, but then you would only capture, and that's the problem, you would only capture the part down here, right?
No, I don't want to do an amplitude expansion. What I want to do is write the full dynamical system for how many dimensions I have for these modes, and then study its bifurcations. And ask how many modes do I need to keep until I can approximate this bifurcation diagram. And once I know that, then I don't have to get any more, and I've changed it into a finite dimensional problem.
You actually hinted at that, right? That when you talked about how you get from on the dashed line,
I mean,
you have the highest stable eigenvalue.
I think the problem is you can reconstruct the diagram, but you would never get these sharp corners that are a conflict angle. So, what other people, what like landed for coarsening problems is more that you actually take a system of many drops and you get an ODE system for the center of mass positions and the volume of the individual drops. And then you can describe coarsening. I think you could not come to this with that proposal because you would, let's say, expand in Fourier modes, and so you could never catch, I think, the dynamics that droplets exchange mass through a precursor film or so, because you would, by definition, stay sort of softly modulated. Or do I misunderstand this? Sorry?
You could answer this numerically by running Fourier modes for the full set of Fourier modes, and then keep only some number of Fourier modes from the big calculation, okay, and let those drive the rest of the modes.
Actually, we might be able to answer that question in 2 months, because we try to do some numerics based on the Fourier decomposition, and because we want time periodic states.
So the question is whether the higher modes are slaves to the lower modes in some sense.
Yeah, I mean, I would be skeptical because of this sharp. I mean, you see these are still rather sharp, so this has a because film of height 1 and the droplet is 150 here. So, I mean, you run into trouble in the corners, I would say.
Thank you.
Other questions?
But if you go back to the diagram where you show in one range where you have the instability dominated versus the nucleation dominated. So what's actually going on in the metastable range if you just initialize it with something top-like? I mean,
You mean with drop-like or with a film with a dent?
well, either way. So basically,
With a dent, it depends then on the size of the dent. Right. So if the dent is too small, it becomes a flat film.
I just wondered if it stays localized or if it will also form these wiggles like in the next diagram.
Oh, that's a good question. Let's say, I think no one really analyzed the secondary nucleation process systematically. Because I would expect that at some point, I mean, there is a typical size of this, there is a typical size of this dynamically produced dimple here, you could say. And if this typical size is smaller than the critical nucleus, then you will just have a single hole that grows. But if this dimple is larger than the critical nucleus, then you will have the secondary nucleation. But I'm not aware of a systematic study. Because I'm also not aware of many experiments that show these nice secondary holes. I mean, actually, I'm not aware of the second one.
I think perhaps we should stop at that point because with the
Coffee is
mistake.
great, yeah.
And we'll